soon as it finishes, which it's now recording, let's get started. Okay, where we are in Chapter 2, First Order Differential Equations. Oops, here comes Kira. So let me get her here. Okay, and Kira, we're just about to get started. Did you have any questions or issues or problems, concerns? Okay, so here we go. Where we left off last time, Chapter 2, First Order Differential Equations, Section 2.6, the last section in this chapter, a numerical method. It's just a numerical method. There are several numerical methods out there. This is the one that the book is showing at this point. I think in a later chapter it shows into more detail others. I don't think we'll get there, so this will probably be our numerical method for now. Not that you have to use it that much, but now, if you recall last time, we were looking at a function in example 2 that we didn't have to do numerically because we knew how to calculate the analytic solution, the exact solution. We did that with step size of 0.1, which you see here, and with step size of 0.05, which you see there. Okay? Now, they're talking now. We did that. We did several of those. We didn't do them all, but we did several of them. Showed you how to present those. Okay? The things to pay attention to, of course, at the beginning, the initial value when x equaled 1, y was equal to 1. So there you have it. Okay? Then the next step size, 1.10, this got us up to 1.02. It took 2 steps to get there here, 1.0206. So they're still pretty close together. Here's the actual value here. Okay? 1.0212. So you see the 0.1 step size gets you off a little bit further than the 0.05 step size. In fact, you're half the distance from this that you would be here. When you get up to 1.2 here, your y-sub-n that you calculated was here. The actual value's here because we can calculate this, off by 0.0025. So it's still very, very close. But here, 1.2 has you only off by 0.0013. Again, just about half of what your error was here. 1.30, the error has moved up to 0.004. Over here, it's only gone to 0.002. So again, exactly half. 1.4 here, your error is 0.005. Still very, very close. Here, 1.4 is 0.0028. Wait, am I right? Yeah, 28, which would be, again, very close to half the error. Okay, and 1.50 here, you're off by 0.0073, which is pretty close. Okay, here you're, again, very close to half of that. Now, that's your absolute error. What is absolute error? It's the actual value, no, I'm sorry, the calculated value minus the absolute value. Okay, absolute value, the known value. Now they're doing absolute error, which is the absolute value of that. Okay, so you always get positive numbers here. So it doesn't matter which one you subtract, it's going to come out absolute value wise the same. But you see the absolute error is about half here of what it was there because your step size was about half here of what it was there. So that's not a guarantee, but it sounds reasonable. Okay, now your percentage relative error is this. Okay, well, let's go to relative. Well, relative error is the absolute error that you got here divided by the absolute value, the actual value. Okay, these were all positive, so they were absolute. So you divide the error by the known amount, the amount that you know to be true. Now, a lot of your things that you'll be doing numerically, you don't know the answer. That's why you're doing them numerically. So you won't have the advantage of that. But this is showing how this pans out. The relative error is then take the absolute error, divide it by the absolute value of the actual value, and multiply by 100. So you see, this is just move your decimal 2 places. It looks like they messed that one up. Okay, it really does look like they messed up here. This is correct. That's good. That's good. I don't know how they got off here. That's good. I don't know how they got off there. That's getting a little further off. It looks like, I don't know. It's basically multiplying this by 100. How do you get 5 decimal points off? I don't know. I do not know the answer to that one. The key here is, oh, I'm sorry. This is they didn't list the relative error. They only listed the percent relative error. That's how it happened. So they didn't do, I was thinking this was percent error. I mean the relative error. This is the absolute error. The reason they're close is these numbers are close to 1. Okay, so that's why they're close. So my bad on that one. So that's just how you do that. Now here's the caveat. Something to keep in mind. Euler's method is just one of many different ways in which a solution of a differential equation can be approximated. Although attractive in the simplicity, it's seldom used in serious calculations. Okay, it's introduced here just to give you a first taste of numerical methods. We go into greater detail in discussing numerical methods in Chapter 9, and the ones that give significantly greater accuracy, the 4th order Runge-Kutta method, or RK4 they call it. Okay, now, because it's mentioned here, you certainly could write who in the world was Runge, or who was Kutta, by the way. They must have worked together, or they worked separately and they came together, however that happened. And how did they develop this, and what are advantages over Euler's method? They're going to show you that in just a minute. Okay, now that's one way. They also have what they call numerical solvers, which to me is a numerical approximation. And they really don't go into great detail here, and I wish I could remember for certain what the titles are. There's 2, and the names are very similar, and they give very similar results. One gives a little better on one type of problem, another on the other. One is the finite difference method, and the other is the finite, or the I can't remember, but there are a couple ways to do it. And basically what it is, you do it on a computer. You have the computer do the analysis for you, and you, let's see, I don't think they're going to show you another example, but I will just give you a real quick and dirty if they show. Okay, here's one. Okay, here would be your the one we were just doing, I think. Yeah, that's it. This differential equation is dy dx is equal to 0.2 x times y, with initial value y of 0 equal to 1 on the interval 0 to 4. Now this isn't quite the one we did before, because we did when x equal 1, y is equal to 1. So it's not the same form, but it's close. Okay, it's similar. Now, the Euler's method you saw always undershot, and the further you got from that initial place, the further you are away from the actual value. The RK4, or Runge-Kutta 4 method that they were talking about here, it attaches itself, so to speak, to the function at 4 known values, or at least this one does. Actually 5 if you count this endpoint. Okay, but the problem with that is a lot of times you don't know the exact value. So how they get that, you'll have to wait or look at chapter 9 and see. Okay, but you see, by and large, it gives you far, far closer approximations. Okay, now what I was talking about, finite difference or finite, I can't think of the other name for it. This would have been dy dx is equal to 0.2 xy. Okay, and with that initial conditions, that would be your starting point. Well, what you would do then is make this, choose a step size, just like we did with Euler's method. To start with, say 0.1 or 0.05, wherever we want to start. Choose a step size, and then do a change of y per change of x. The change of x is that, so you can multiply through by that, and then go through a lot like we did. But then once you had done that, then decrease your step size by, say, half. Take half of it, and then do it again. And after a certain amount, look at the two answers. If the two answers are within whatever tolerance you're really willing to stand, 0.1, 0.01, 0.001, whatever it is, you just keep running the analysis, finite differences, until you get so that two consecutive answers are within your tolerance. And then you say, hey, that's close enough to me. Okay, I know that was a really quick and dirty, but anyway, that's how you do these, and they mostly have packages that will do that for you. You don't have to do it from scratch. When I was a grad student, I had to write my own programs in BASIC, I believe it was, and estimate my differential equations, and some of those were actually partial differential equations, but we tried to keep it as much as possible to ordinary. Now, they do point out some of the problems with you, and that problem is, in a numerical solver, sometimes you can get some wacko type results. You know this isn't true, and yet if you happen to choose just the wrong step size for your particular problem, and your problem is a rather bizarre one, then it can give you some results that look like this, which are ludicrous. Okay, so you just have to watch it. Sometimes the numerical solvers will work, and sometimes they get kind of off. Okay, so they call this a not very helpful numerical solution curve. Not much of a curve either. Well, that finishes 2.6. Any questions on 2.6? All you're responsible for is Euler. Okay, now, sorry about that. I just ate an apple. Some of it stuck between my teeth. Sorry about that. Okay. In 2.6, homework exercises, do number 1. I think you can find it in the back of the book. Now, is that someone coming in, or did I just hit something down there somewhere? I think it's just the two of you and me. Okay. Wow, pretty low attendance today. I was hoping more would be here by now. Okay, to do number 1 if it's in the back of the book. Do number 3 if it's in the back of the book. Do any of the odds 5 through 9 if they're in the back of the book. Do number 11 if it's in the back of the book. And that's it. The rest of them are discussion or computer lab assignments. If you do have a computer program like CAS or something like that, and you want to play with it, play with it. I don't have one, so I can't assign those to you. Alright, so that finishes chapter 2. Now here you have some additional problems, and answers to selected ones of these are also in your back of the book, the back of your book. So you can look at any of the odds, because they only have odd number answers back there. Any of the odds 1 through 11, 13, 15, if the answer's in the back of the book. Not in the back of the book, don't worry with it. Okay? 17, somewhere down here is not, yeah. Any of the odds 19 to 25. Now this is only if you want more practice. Here they are. Okay? Either 27 or 29. 27 is at the bottom of this page, of this column. 29 is at the top of that one, right there. 31, if they have the answer to that in the back of the book. 33, if they have that one. And then I would say 35 and or 37. Do either one of those. 39, if that's in the back of the book. And I think that's it. Okay, let me go back and make sure I didn't skip. Oh, that went too badly. Okay, yeah, that ended at 39. Now, some of those aren't in the back of the book. Don't sweat them. Okay, now, we finished chapter 2. There's nothing in our course description that I remember that had anything to modeling. Not that this isn't important stuff, and it's interesting stuff, and it's a fairly short chapter. We just don't have time to do it. Okay? If you think your major requires something like this of you, it's a fairly short chapter. I think not that bad of reading. I don't know what all these noises are. Let me make sure someone's not trying to come in. Nope, just the two of you and me still. So we're going to skip chapter 3. Okay? Now, again, you're welcome to look at it if you'd like. I'm going to close up chapter 2 here because it's just taking up space. Okay? And we're moving on to chapter 4. Okay. So skip chapter 3 and in very short order. Now, anything you see in 3, as in people's names, properties, operations, anything like that, if you see something there that's of interest to you, could be a potential paper topic. Again, scan your book for paper topics. Okay, I thought I checked on this. I guess I didn't. Okay, here we go. So here's chapter 4, higher order differential equations. Okay, pretty picture there. Now this is one long chapter. Okay, we're going to start with that preliminary theory, and unfortunately that always takes too long. It doesn't seem like you're really getting anywhere on it, but we'll do that. We'll talk about reduction of order. That's a fairly short section there, and then we'll start into 4.3 on homogeneous linear equations with constant coefficients. Now, if you think you know what homogeneous equations are, when we talked about them in chapter 2, that's different from what they're talking about here. We'll go back to the more of the standard way of talking about them here. So we'll do 4.3. Then we'll do 4.4. Now 4.4 and 4.5, you can do either one of two ways, superposition or annihilator, but you don't have to do them both. Okay? Now I've taught them both, and it seems to me that students tend to understand the superposition approach more easily than annihilator. They really aren't that much different, but there is just the fact that we've done superposition in other contexts. We'll just go with that. So we'll do 4.4, skip 4.5. Then we'll get into variation of parameters. Okay? Unfortunately then, we'll begin to run out of term. So however far we can get in chapter 4, that's probably going to be it for this for the course. I'll go back and check the new course, not description, but it includes the description, but course outline that the state came up with, and see if any of these things, they are skipping, and if so, we'll go on and skip those. But I know we'll do the first, second, third, fourth, and sixth, and then I'll judge from what they say which of these others we'll go to. Again, I think we'll run out of term before we run out of course, so we'll go from there, which probably leads you to think, quite rightly so, some of these are going to take quite a bit of time and effort. Okay, they're not going to go fast. So we now turn to the solution of ordinary differential equations of order 2 or higher. Chapter 2 was first order differential equations only. Now we're going to be doing second, third, fourth, whatever. The first 7 sections of this chapter, we examine the underlying theory and solution methods for certain types of differential equations, linear differential equations. The chapter concludes with a brief examination of solution methods of nonlinear. So I don't think we'll get to the nonlinear at all. I'll even check and see if they even want us to do those. Okay, but that's down here. Don't think we're going to get there. Okay, so let's start with 4.1. And again, when they start these first ones, say preliminary theory, usually it takes so long for them to get anywhere because they talk in generalities. They talk around the subject without telling you anything very specific. But it's sort of necessary for what they're going to do later. So here's the preliminary theory here. Back in chapter 2, which we just finished, we're able to solve a few. Whoa, here comes James. Good deal. We've just increased the class size by 50%. So James is here. So now we got over half of us here. We're missing Ryan and Jesus. So hopefully they'll be coming in. James, it's good to have you. I don't know if you are hooked up yet. Looks like you are. Okay, good deal. So we're beginning chapter 4. We finished what little bit we had to do in chapter 2, skipping chapter 3, moving on to chapter 4. Chapter 4 is dealing with higher order differential equations. Remember, chapter 2 was linear, first order differential equations only. Chapter 4 is preliminary theory for higher order differential equations, but we're still here only going to deal with linear equations. We don't get into higher order equations with exact. I don't even know how you would do that. Okay, that doesn't seem to ring a bell. Separation of variables would be very difficult to do in higher order differential equations. You just can hardly do that. Basically, linear equations are where we're going to stay, at least for now. Okay. So chapter 2, we're able to solve a few first order differential equations by recognizing them as either separable, very easy, linear, we're going to continue that, exact, okay, that had its promises, but when you move to higher orders, that's going to be hard to do. And having homogeneous coefficients, and we dealt with that one too. Even though the solutions obtained were in the form of one parameter family, that family, with one exception, did not represent a general solution of a differential equation. The general solution is a family of solutions defined on some interval I that contains all the possible solutions of that differential equation on that interval I. Only in the case of linear first order differential equations were we able to obtain a general solution by paying close attention to certain of the continuity conditions imposed by the coefficients of that equation. Because our preliminary goal in this chapter is to find general solutions of linear higher order differential equations, we need to examine some of the basic theory of linear equations. All right, blah, blah, blah. We're going to start by sort of a contrast between initial value problems, which we've done before, and boundary value problems, which we haven't done. but this is going to be in the context of higher order differential equations. So here's the initial value problem that we run into. And it's not a big problem, it's just something to keep in mind. Section 1.2, we define an initial value problem for a general nth order differential equation. So we did do higher order there, nth order, for a differential equation of nth order initial value problem, IVP. Here's how it looks. Solve this. This is a functional coefficient, not just a numerical coefficient, a function, coefficient function, a sub n of x. Now this sub n here has absolutely no bearing on your solution or anything else. All this is an identifier, and that identifies that this numerical or functional coefficient corresponds to the nth order derivative. That's what that n stands for. This is the function that goes with that derivative. This is the function that goes with that derivative. And so on down, this is the function that goes with the first derivative, and this is the function that goes with the zero derivative, which is the function itself, okay, the y. And that's equal to some g of x, okay? Now, we probably mentioned that, talked about it some, but we were only doing first order differential equations, so we didn't go any further than that. Now, when you have a higher order initial value differential equation, you need more initial values. For a first order, all you needed was some value of y at some fixed value of x. That's all you needed. First order differential equation, you needed one initial condition. For an nth order differential equation, you need n initial conditions. Of course, you need that first one. What is the value of y at some fixed value of x? The next one, though, you need is what the value of y prime is at that same value of x, okay? And then, what is y double prime at that same value of x? Then what is y triple prime? All the way up to the n minus first derivative of y at that same value for x, okay? Now you say, wait, aren't we missing one? I thought you said we had n. Notice we started with x sub 0. 0, 1, 2, 3, 4. That gave us up to fifth order. Okay, so yeah, we don't need. We only go to the nth, n minus 1 difference, boundary initial value, n minus first derivative for your initial value, even though it was an nth order differential equation. Okay, you have your n initial values. Now recall that for a problem such as this one, we seek a function defined on some interval I containing that x sub 0, has to be there, that satisfies the differential equation that, okay, and the n initial conditions, all n of them, okay, specified at that same initial value, x sub 0, okay. We've already seen that in case of second order initial value problems, a solution curve must pass through the point and have the same slope. Now that was back in section 1.2, but we were only doing first order equations in general then, though we did show that's the case. Now, remember we stopped a couple of times and talked about existence and uniqueness. In section 1.2, we stated a theorem that gave conditions under which the existence and uniqueness of a solution of first order initial value problem was guaranteed. Guaranteed. The theorem that follows gives sufficient conditions for the existence of a unique solution of the nth order differential equation, not just first order, nth order. Now notice here, gives the following sufficient conditions, whereas up here, sufficient conditions for a unique solution. So this dealt with the uniqueness. You wonder if the existence, I think that's also included here. So let's move on and see what it's, whoa, I just blew that, but it doesn't really matter to what we're doing here. I thought we were on this scale. So here's the theorem. And boy, this has been happening all day long. Oh, yeah. Okay, my wife just texted me, so I had to at least read that one. Okay. Here is the existence of a unique solution. Okay. Let a sub n of x, a sub n minus 1 of x, a sub n minus 2 of x, down to a sub 3 of x, a sub 2 of x, a sub 1 of x, a sub 0 of x, and g of x. All of those functions of x and x alone that we had up here. Here they were. This was a coefficient function, coefficient function, coefficient function, coefficient function, coefficient function, and then your solution function. Or your, okay? All of those are continuous. If those are all continuous on that interval I in which your x sub 0 is located and on which this differential equation is defined, and as long as that first one, the a sub n of x, is not 0 for any value of x on the interval. Now, why is that true? Because if that were 0, this is not an nth order differential equation. Okay? We're saying it is an nth order, but if that was 0, it would not be an nth order. Okay? So, and there's another reason, we'll get to that later. For every x in the interval. Okay? If x equals x0 is any point on that interval, then a solution y of x of that initial value problem, this one up here, right here, that initial value problem, does exist on the interval, and not only does it exist, it is unique. Okay? So here's example 1. Here's an initial value problem. Okay? Third order differential equation. Okay? 3y triple prime plus 5y double prime minus minus y prime plus 7y equals 0. Okay? Now, we know that y at point 1 is 0, y prime at point 1 is 0, and y double prime. Third order differential equation, 3 initial conditions, beginning at the function and then only doing the first and second derivatives. You never give your third derivative as an initial condition. The nth derivative is an initial condition. It's always the 0th, first, and second derivative. Okay. Now, you know that this one, just looking at it, y is equal to 0 is going to make that true. 7 times 0 is that. Y prime is 0. If y is 0, y prime is 0. Y double prime 0. Y triple prime 0. You know that's the solution. Now, because that third order differential equation is linear, in other words, there's not any y primes in with this y triple prime, no y squareds in here. You know, they're all linear in that there's no products of functions of y in there. You, with constant coefficients, 3, 5, minus 1, and 7, it follows that the conditions of 4.1.1, which is what we just looked at, let's remind ourselves what they are. These are continuous, these x's, well, those are constant, so they're continuous. On the interval I, of course they are. A sub n of x, 3, is not 0, can't be 0 anywhere, it's 3, for every x in the interval, and then that 1 is in the interval of interest here. It possesses that. Because all the conditions are met, it follows that the theorem 4.1.1 are fulfilled, so therefore that y equals 0 is the only solution. Don't look for any others. You will not find them. on any interval containing x equal 1. That's it, folks. That's all. The theorem tells you that's going to be the case. Okay, let's move to example 2. That was way too easy, wasn't it? Okay. How about uniqueness of an initial value problem? Okay. Now, here's your function. Here's your solution. Y is equal to 3e to the 2x plus e to the minus 2x minus 3x. Okay. They claim that that function is a solution of this initial value problem. Y double prime minus 4y is equal to 12x. With this initial condition, y of 0 is equal to 4 and y prime at 0 is equal to 1. Second order differential equation, you need two initial values. One is the function, the other is the first derivative. You never do the second derivative. Okay? So, constant coefficients here, continuous function there, everything fits. So the first thing we want to do, verify that function is a solution. Once we know if it's a solution, then we'll determine if it's the solution. Okay? So let me go to the whiteboard and we will do the first. Find out first if it is a solution. This is sort of like you did for your first test. Now what I'm going to do now is move y'all to the right here as far as I can. Move this box as far up as I can. And move the whiteboard as far to the left, is not moving, to the left and up as I can to give me the most white space to write on. That's the only reason I do this. Okay. So this is example 2 on page 120. Here is your proposed solution. They say it is. This is what we're going to verify. Let me get it in my lap because it's sort of hard to read from a distance. Okay. Okay. Y is equal to, will not draw equal signs well, 3e to the 2x, 3e to the 2x plus e to the minus 2x minus 3x. They say verify that's a solution to this differential equation. Y double prime minus 4y equal 12x with this initial condition, these initial conditions, y of 0 is equal to 4 and y prime at 0 is equal to 1. Okay, so we know the initial value and the initial first derivative. Okay, now how do we verify? We first have to take a derivative of this function here. Excuse me just a minute. I don't know if I got something in my eye or it just suddenly started aching like crazy. Don't know why. Okay. Goodness, I can hardly see now. Okay, let's do the math here. Y prime is equal to 3e to the 2x times 2 by the chain rule. So that would be 6e to the 2x minus, I know it's going to be a minus when I do that, 2e to the minus 2x. You check me and make sure I'm doing this right. And take the derivative of that, you get a minus 3. You know, we really didn't need the first derivative because it didn't show up here, except that you have a second derivative here, and you can't get the second derivative without doing the first. So now let's do that second derivative, y double prime, and that would be equal to, I'm sorry, my eye is just killing me. It just all of a sudden started hurting, and I have no idea why. Okay, y double prime would be, where's my pen? There it is, 12 with the chain rule, 12e to the 2x plus 4e to the minus 2x. I'm doing it rather quickly, and then this gives you nothing. So let's plug this in here for y double prime. 12, I left off my x here. Why is that? I said it but didn't write it. 12 e to the 2x, maybe that's what happened. I went to write it but nothing happened. Plus 4 e to the minus, okay, 2x, that's all that is. That minus 3 is part of that problem, not part of this one. Okay, so that's that. Minus 4 times the function itself. That's what we had here. That's 3 e to the 2x plus e to the minus 2x minus 3x okay, 4 times that. Supposedly this is equal to 12x. Let's see if that's true. This is 12 e to the 2x plus 4 e to the minus 2x minus, distribute this, 12 e to the 2x minus 4 e to the minus 2x plus 12x is equal to 12x. Is it? Well, here you have a positive 12e to the 2x. Here you have a minus 12e to the 2x. They add to 0. Here you have a plus 4e to the minus 2x. Here you have a minus 4e to the minus 2x. Those add to 0, and sure enough, 12x is equal to 12x. So, we verified that is a solution. Okay. Now, that's a solution. Now, the differential equation is linear, right here. Right there, that's linear. Or any y's multiplied by any other form of y. Okay? The coefficients, 1, minus 4, and the function over here, 12x, are all continuous. The a2 of x, which is right here, 1, is not equal to 0. Got it? On any interval I containing x equals 0. That was our initial condition, x equals 0, if I could get it here. So no place there are they not continuous. We conclude that that is a unique solution on I. That's all they say. Because we've verified it is a solution, it has to be the solution, unique solution for that differential equation. You can't find any other function anywhere that won't fit those criteria right there. That's it. That's all, folks. Okay, excuse me just a moment. I think the anemia is setting in. I'm just running so out of energy. Hold on. I can't recall if all of you were present in the last class. I know you were there, but when I gave sort of my synopsis of how things are going to pan out now, but let me just tell you, I'm scheduled for tomorrow and Friday to have treatments. 10% tomorrow, 90% on Friday. I go in tomorrow morning at 7 o'clock, be there at 7 o'clock, and they say they've allowed me about 8 hours. I'm hoping it won't take that long. But just to be, they're going to be very slow and careful, make sure I don't have any adverse reactions in order to maximize the case that I won't have any adverse reaction. In other words, minimize the possibility of having any adverse reaction. They're going to give me at least Tylenol to keep fever down, at least Benadryl to keep me from having a reaction to it, and steroids to, whatever steroids do, stimulate your ability to handle things like this, I guess you would say. Okay, they're going to do all that and give me 10% of the dosage tomorrow, and if everything goes well, then they'll do 90% on Friday. Now, the last time I had this, or every time I've had this drug, I haven't had any problems at all tolerating it, none whatsoever. The reason they're a little concerned here, and the first time I had it, first time ever having it, they did do the same thing, 10% on one day, 90% the next day, just to make sure I wasn't going to have any adverse reactions. Now, every other time they just give me the full dose in one day. The reason they're doing this one is my white cell counts are so incredibly high. Okay, so they have had situations with high white cell counts. This drug knocks it out so fast and so well that you wind up with all sorts of junk in your system of the destroyed cells. Okay, and it's hard for your system to clear them out fast enough. So they've got me on a diuretic now. But here's what I was getting at. I'm starting this time with really low hemoglobin, this anemia. And it has nothing to do, they don't think, with the disease or the treatment. It's just that the white cells have suppressed the manufacture of red cells in my bone marrow probably. And the platelets, same thing. So I'm starting off at a deficit for red blood cells. Every time I've had this treatment, it also lowers red blood cells. So it could be next week, even though probably my white cell count goes down big time. It always has with this treatment. It could be my red blood cells go even lower too. So you may not be through with me having no energy. Okay, that's what I'm trying to say. I'll try to hang in there as best I can, but we'll see what happens. All right, sorry about that, but I didn't know if all of you there. Seems like my phone keeps making noise. No, it's not. Okay. Now, let's go back to the text. Okay. Still only 3 students here. But 3 out of 5, that's not too bad. So what we've just done, I'm going to move y'all again. The text, you're better up top. The whiteboard, you're better on the side. Okay. So we did this. We did verify it. The differential equation is linear. Okay. The coefficients as well as the g of x here are continuous. The a sub 2, 1, is not equal to 0. So therefore we can conclude that from the theorem, all the conditions are met. This given function here, which we just verified to be true, is the unique solution on that interval I, wherever that interval was. And I can't think of any reason that would not be all real numbers. Okay? Because there's nothing in this where if you plugged in a value for x, you would have anything but a continuous function. So it looks like it's good. Now the requirements of that 4.1.1, that all of those coefficient functions be continuous and that first one not equal to 0 for every x in that interval I are both important. Specifically that one that says that a sub I of x cannot be 0 for any value of x on that interval, in that interval. Then the solution of the initial value problem may not be unique or even exist if those conditions aren't met. For example, here's a solution of a differential equation. Let's write it down. Let's go back to the whiteboard. Okay. We're running out of it. Okay, let's move. Kara, move back to the right here. There we go. And I probably need to scoot you down a little bit too. Okay, now we're good. All right, to erase this. Okay, I'll clear all that work. And let's see where we picked up here. Okay, here again is a proposed solution. Y is equal to cx squared plus x plus 3. Okay, C looks a little suspicious, and that's going to be a hang up here. And this is supposedly a solution for x squared, y double prime, plus 2x, y prime, plus 2y is equal to 6. Okay, with the initial condition that y of 0 doesn't write equal sounds well, is equal to 3, and y prime of 0, you need two initial conditions because it's a second degree differential equation. Y prime at 0 has to be at the same value, is equal to 1. Okay, now what we need to show, just like before, is that this is a solution to that. So we start by doing y prime is equal to 2cx plus 1. That's it. That's all of it. Okay, y double prime is equal to 2c. That's it. That's all, folks. Okay, now let's multiply this. Y double prime 2c, that would be 2c y prime. I forgot my x, and I wrote the wrong prime. I'm trying to find my eraser. My brain is fading fast. Okay. Goodness gracious, I'm so tired. Okay, I'm going to have to get me another sip of something here. I feel like I'm living on caffeine and sugar now, and that's not good. I don't like taking either one of them. Your y double prime is 2c, multiply that by x squared, plus 2x times y prime. I'm going to try to do this as I go. That's 2 times 2 is 4. C x squared, that's the 2 times this term, 2x times this term, plus 2x times this term, plus 2x. I hope you were able to follow that. 2x times this whole thing here would be 4cx squared plus 4c, wait, plus 2, goodness gracious, plus 2x, okay, plus 2x, and that's what we got there, okay, plus 2 times your y. So that would be 2c y squared. No, I'm sorry, that's x squared. I can't read. Goodness, I'm losing it, folks. Wait just a minute, sorry. Sort of the good news is tomorrow, while I'm taking the treatment, I'll be grading papers up until the Benadryl sets in. Okay, once it does, I'm out. So I hope to be able to sleep and just sleep and sleep for most of those remaining 4, 5, 6 hours, whatever it is, after the Benadryl takes effect. I'll grade papers as long as I can, then I'll do that. So hopefully I'll get some things caught up on grading, but then I hope to sleep. Okay, same thing on Friday. I'll grade as long as I can, and then I hope to sleep. I hope to get home and be able to teach the second class, my last class, the 4th class tomorrow. We'll see how that goes, okay? But I hope that I will have slept enough that I could do that, and then I hope that Friday I'll just sleep. And when I get home Friday, I'll probably go right on back to bed and sleep some more. So hopefully I'll get rested up. That's one thing. But I don't know with the anemia if I'm going to be just as exhausted. So we'll have to see. So we're doing 2 times y. Where is my pen? There it is. 2 times y. Here's your y. So it's 2c x squared plus 2x plus 6. 2 times 3 is 6. The question is that equal to 6? Okay, well, let's see what we've got here. I must have copied a sign wrong or something here. Yes. Okay, cx squared plus, okay, that's right. Ha! There's where my error was. Sorry about that. That's a minus there. Whoops, I lost my 2 too. Minus 2. xy prime plus, okay. Alright, that changes a lot. This term stays the same. This one becomes a, let me see. Here's your double prime. Okay, that's 2x squared y, 2c x squared. Got it. Minus 2x times y prime. That would be minus 4x. So why did I get rid of my eraser? That's going to be a minus 4cx squared minus 2x. Now I think I can get rid of the pen. Plus 2cx squared yuck, this thing just drives me nuts, plus 2x plus 6. Okay, that works. Alright, so let's see what we got. Here's a 2c x squared. Whoa, here comes James. He must have had to get out and come back because I already have him present. Don't I? Yes, I do. Okay. Now, so there's a minus 4c x squared But here's another plus 2, so these two 2cx squareds add to 4cx squared, minus 4cx squared adds to 0. Here's a minus 2x, there's a plus 2x. They add to 0. 6 equals 6, yes. We know this solution satisfies this differential equation. We verified it. All right. Now, what's the point here? Okay. Now, let's also check and see when x is equal to 0 if you get y is equal to 3. Well, you plug x equals 0 in here, you get 0 plus 0. Sure enough, y is equal to 3. So that checks. Okay. Then do the y prime, here it is, and when x equals 0, that gives you 1. Yes, that checks. So not only is this differential equation met, the boundary values are met. And yet we have a c in the problem, meaning for any value of c, it's a different solution. Well, how can this be? How can this be? Well, here's how it can be. Look at this. Your x value here is 0. If you put an x equals 0 in here, you have 0 squared, which is 0, times y double prime, which is 0. That is not a second order linear differential equation. That first coefficient is a value of x, specifically your initial value of x disregards or contradicts what your initial condition, what your theorem stated had to be the case. No value in your interval can make that initial coefficient function equal to 0. The very one you're going from made it 0. So that's why that did not fit the bill. Okay? Now, let's go back, I think, to the book. All right. Goodness gracious, I'm tired. Okay. Now, I thought I saw something like someone pop up. Did they? No, still got 3 people here. No one's waiting. Okay. Now I'm going to move y'all out of the way again. Jemanuel, move out of the way again. Okay, here we go. So we saw that this, even though it looks like an infinite number of solutions here, rather a unique solution, the reason it didn't is that your initial condition here called for x to be 0. If x equals 0, the function is not a second order partial differential equation. Okay? So let's move to the concept of boundary value problems. Now, I really don't know exactly why they put this in here. Okay? Certainly it is something you concern yourself with, but we're not going to deal with it, I don't think, at all anywhere but this little place right here. But maybe they have to deal with it, so that's what we're going to do. So, what do we mean by a boundary value problem? Another type of problem consists of solving a linear differential equation of order 2 or greater, in which the dependent variable y or its derivatives, okay, are specified at different points, not at the same point. So here would be, I'm so sorry, an example of this. Here's your differential equation. There's your coefficient function a2 of x, d2y dx squared, second order equation, plus a1 of x dy dx, plus a0 of x times y equal g of x. Good old second order differential equation. Subject to y at a. Now this a has nothing to do with those a's. I wish they had chosen a different letter, okay? It has nothing to do with that. But y at some value is equal to y0, but y at this other value, not a, is equal to y1. Okay, well, guess what? We've got our two conditions met. It's a second order differential equation. We've got two conditions, but they're not initial conditions, because A can't be your initial value and B the initial value if they're not equal to each other. So that's called the boundary value problem. One thing is justified here, another thing is justified here. X equal A, X equal B. Okay, that's a boundary value problem, the BVP. The prescribed values, x of A is equal to y0, y of A is equal to y0 and y of B is equal to y1 are called the boundary conditions, BCs, not before. Okay. A solution for the foregoing problem is a function satisfying the differential equation sorry, goodness, my head is messing with me. Oh, man. Okay. A solution to that problem is a function satisfying the differential equation on some interval that contains both A and B and whose graph passes through both of those points. When x equal A, y is equal to y0. When x equal B, y is equal to y1. However, for a second order differential equation, other pairs of boundary conditions, well, wait, okay, here's the figure here. These could all be solutions for that differential equation, but the boundary values say at x equal A, y's got to be y1, at x equal B, y's got to be y2. So let's just say those are it. Well, this curve and that curve fit the bill, and those are different solutions. So when you have a boundary value problem, I don't want to say you can't have, but fully expect not to have unique solutions. You may find solutions, but the odds are they will not be unique. Okay? Now, whereas is pretty well designated what your initial conditions have to be. They have to be at the same point, not A and B, just one of those others. Say at A. Your y of A is this, your y prime of A is that. If it's a second order differential equation, that's it. I mean, what the values are doesn't matter, but y of A has to be defined and y prime of A has to be defined. But with a boundary value problem, just like we had here, you could say y of A and y of B. Or you could say y of A and y prime of A. Well, that would be an initial value problem. You could say y of A and y prime of B. Oh, yeah, that's a boundary value problem. Or y prime of A and y of B. Another boundary value problem. Y of A, y prime of B, y prime of A, y prime of B. There are basically 4 sets of potential boundary values that you could have for that one differential equation. Okay? Those 3 pairs of conditions are just special cases of the general boundary value condition. Now, this introduces a really strange notation here, but it certainly does work. Alpha 1, okay, of y times y of A plus beta 1 times y prime of A is equal to gamma 1. Alpha 2 times y of B plus alpha 2 times y prime of B is equal to a gamma 2. Okay? Now, notice if you have two well, let's not spend too much time on it because frankly we're hardly ever going to use it if we ever do. The next example shows that even when the conditions of theorem 4.1.1 are fulfilled, the boundary value problem may have several solutions, a unique solution, or absolutely no solution at all. So that's what they're going to be showing. Let's let them see what it looks like. Now, we only have 3 minutes. Let's see what we can get covered in the 3 minutes. Example 3. Okay? Bottom of page 120, top of page 121. I think I'll go to the whiteboard, and we'll probably run out of time before I get too much done on it, but let's try it. Okay. It's example 1 of section 1.1. We saw that the two-parameter family of solutions of differential equation. Let me go on and erase this. Does anyone need this any longer? Okay. Gonna move y'all back down where you were, James. Get out of the way there. Okay. Here is your differential equation. X double prime, now that's not how we're used to seeing it, plus 16x is equal to 0. Okay. A solution to that would be x is equal to C1 cosine of 4t plus C2 sine of 4t. I can't write. Yuck. Let me try that again. This is... I can't erase either. Well, literally I can't erase. The eraser's not coming on. Sorry about that. That was a 4t. Okay. Sorry about that. And we're out of time anyway. Sorry about that. That's just completely flubbed up at the end between my writing, the pen's activity, or whatever. Hold on a moment here. Let me erase my mark that I had here and indicate that we'll start working with example 3. So we'll start all that over again. Let me get my paper in place. And your homework exercises here, we didn't get very far along. And this is one long section, folks. We may be here a while. Do either 1 or 3. They should both be in the back of the book. Okay? Try number 5. I think you should be able to do that one. Okay, I think you probably can do 7. I think you may be able to do 9. Okay, maybe you can stop somewhere around there. We'll pick up on those somewhere else. Any questions? Goodness gracious, I'm running out of energy. And I've got to head out, so I do need to leave really quickly. Okay, any questions? All right, I'm going to end the meeting for all of us then. For those 3 of you, no, 2 of you, I don't think one of them was here today, that normally we'd be meeting tomorrow, not meeting tomorrow. Okay, now if I do get home super early, I may open up a meeting, and if you see it, come on and join. But the odds are I'm not going to get home early enough for that. So anyway, that'll be it for today. Take care. Be safe. I know, beautiful weather, tempted to get out. Be very careful. The virus is still there, and it's still wreaking havoc. Don't let it wreak it on you. Okay? Take care. Bye-bye.